Hello, guys. You're welcome to this lecture on modeling with first-order differential equations. We've already looked at various methods for solving first-order equations, and so this is, if you like, a continuation or an application, different applications to first-order differential equations. But here, I'm just going to look at two main applications. Okay. We'll look at mixing problems. And then in the next video, I'll look at Newton's law of cooling. And then finally, we'll tackle the logistic model. These are just a few of the applications to first order differential equations. Okay. So under mixing problems, this is a setup of the problem. You want to consider two fluids that you are mixing in a tank. So you have a tank, you flow in some fluid. So assume that initially, let's say you have fresh water in the tank, and then you pump in, if you like, salty water or some chemicals into the tank. And then you assume that it mixes up, and then it flows out of the tank. The question is, if x of t here is the amount of substance, all right, that is flowing in. If x of t is the amount of substance at each time t, at any time t, if you like, can you develop a model, all right, that tells you the amount of substance in the tank at every time, at each time? Okay, so that is the setup of the problem. So you need to find R in here, which is the input rate, and then R out here is the output rate. VT represents the volume in the tank. Okay, so you can imagine that if the amount that is flowing in terms of the volume flow rate is the same as the amount that is flowing out, then the volume here will be constant, right, with time. But if what is coming in and what is going out are different in terms of the volumes, of course, then the volume will also change with time. Okay, so that is if you like, a rough setup of the problem we are looking at. Okay, so how do you start by constructing a model for such a problem? Okay, now of course you identify that what you want is that you want the change in the amount per time. So that is the x dt. If x here is the amount of substance in the tank, substance could be a chemical, it could be salt, it could be whatever. How is it changing with time? So what you want is change in the amount per time. Okay. And as I said before in the previous slide, if you want the amount that is changing, of course, it has to do with the amount that is coming in, right? And the amount that is going out. So basically, you want to find the rate that is coming out and subtract the rate that is going out. And that gives you generically a model for the mixing problem. So the rate of change in the amount of substance, the x dt here is equal to the input rate minus the output rate. All right. So the x dt, if you like, is input rate minus output rate. So your task is basically, how do you find the input rate and how do you find the output rate? Of course, your input rate and output rate must be consistent, if you like, with the units here. All right, the x dt has units of x, which is the amount, let's say kilograms, and dt here is time. So amount over time. The input rate has to be put in the same units. It has to be amount per time, and the output rate has to be the same so that each term of your equation or your model is consistent in terms of the units, dimensionally consistent. All right. So you have to look out for that. And so you see a lot of units floating around here. So you have the x dt is R in, which is the input rate, and then R out. So our question is, often this is easier to find, R in, the input rate. We know what is coming in terms of the volume, in terms of concentration. What you have to work out, right? Often what you have to be concerned about is the R out, the output rate. That is what you usually have to be concerned about. Okay. So yeah, this is basically the same thing. The x dt will be R in minus R out. Okay. So as I mentioned, we often know the volume flow rate, which I'm calling Q in here. That is the input flow rate in terms of volume per time. Okay, I know the volume of stuff that is coming in per unit time. So that is usually known. Often we also know the concentration of the substance, okay? Concentration is usually measured in amount per volume, okay? And we know that, which means that if I want the rate, input rate, remember the input rate has to be in amount per time, amount over time. The x dt is amount over time. So your input rate has to be amount over time. So you notice that if I multiply the input flow rate, which is volume over time, by the concentration, input concentration, that is amount over volume, the volumes cancel out and I'm going to get amount over time. Okay, so my input rate, which is R in here, will be inflow rate multiplied by the rate of concentration, all right? Or if you like, the concentration of the flow that is coming in. So the input flow rate is volume over time multiplied by the concentration, which is amount over volume. Volume cancels volume, and I'm left with amount over time. So which means if I know the input flow rate in terms of volume over time, and I know the concentration of stuff that is coming into the tank, I can basically find an expression for the input rate, that is R in, which will be that. Okay, so this will be easy to find. Of course, we're going to do an example of this and you see actual numbers here. Good. Now, remember the model is the x dt is R in minus R out. So we know how to find R in. Question is, how do you find R out? Okay, the output rate. So how do you determine the output rate? Now, similar to what we did for this, for the input rate, if we know the flow, the amount, the output flow rate in terms of the volume that is going out, question is, how do you find the concentration that is going out? You can often use the concentration within the tank, right? You know that you assume that the stuff that comes into the tank it mixes up with the fluid that is already there. Let's say fresh water. It mixes with it. And so if you assume it's well mixed, you know the concentration of that because you know the amount and then you know the volume. So if you know the amount in the tank and the volume in the tank, you can take the amount divided by the volume and that gives you the concentration, okay, of stuff that is in the tank. And that will be the concentration that is flowing out, okay? And so if we know, so here we know the amount in the tank, okay? Let's say VT here is volume of tank, right? And know the volume of the volume of the tank at each time, volume of tank at each time, then C out, all right? The concentration that is going out will be the amount within the tank divided by the volume of the tank. That gives you C out, okay? So if I know the volume that is going out, Q out here, volume per time, and I'm able to find C out here, which I'm expressing as this, then once again, I can multiply the two because of the units. If I multiply the Q out, the volume that is going out by the concentration that is going out, I'm going to get this expression here, and that will give me the output rate. Okay, so the x dt is R in minus R out. R in we're able to find, R out will be given by this expression. So finally, our dx dt will be the R in, which is the input flow rate times the concentration that is coming in. That gives you R in, and this guy is R out. So generically, this, if you like, gives you the model, okay, for such a problem, to be able to determine the amount of substance in the tank at each time. Okay, good. So I hope this is clear enough, an explanation. We'll do an example, hopefully to make it even clearer. Okay, so let's look at an example of how you do that. So this says that a large tank, okay, initially contains 1,000 liters of pure water. So initially you have 1,000 liters of pure water. Salt solution is made to flow into the tank at a rate of 5 liters per minute. Okay, you know the flow rate. All right. The brine solution is mixed well with a solution in the tank and flows out at a rate of 5 liters per minute. So the rate at which stuff is flowing in is the same as rate that is flowing out after mixing. The concentration of the brine is salt solution, right? Of the brine that is entering the tank is 0.2 kilograms per liters. All right, concentration is measured in amount per volume. Okay, so we know that the question is determine the initial value problem governing the problem. All right, the IVP for this question. B, determine when the concentration of salt in the tank will reach this amount, 0.04 kilograms per liter, and how much salt will be in the tank after a long time. All right, what do you mean by a long time? So we'll discuss that. What is the concentration in the tank after a long time? So you want the amount and the concentration after a long time. What do you get? Okay, good. So let's look at a setup of the problem. So these are the numbers from the question, right? Stuff is coming in, Q in, this is my Q in, right? 5 liters per minute is flowing inside. And the concentration of the stuff flowing into the tank is 0.2 kilograms per liter. So that is my C in. So Q in is 5, C in is 0.2, okay? So from the analysis we did before, if I multiply these two, I'm going to get my R in terms of amounts per time, okay? This is the amount in the tank. This is what we want to determine at each time, X of T. In this case, we have the volume of fresh water, initial volume of fresh water in the tank is 1,000 liters, okay? Now the amounts coming in terms of volume per time and amount going out are the same. What that means is that the volume in the tank is going to remain fixed, okay? It's not going to be changing, it's going to be fixed. You have stuff coming in, stuff going out. So the amount there will be fixed, but the concentration will be changing, all right? And the amount of stuff will be changing. Good. So we know Q out, which is 5 liters per minute. The question is, we need to find the concentration, all right, that is coming out as well. That should be able to help us to find R out, right? The output rate, so that we can set up our model, the differential equation. Okay, good. So yeah, so this is what I've just mentioned. The volume in the tank at each time is the same as the initial volume, 1,000 liters. Q in is 5 liters per minute. C in, the concentration that is coming in is 0.2. So my R in, the input rate, will be multiply these two numbers, right? 5 times 0.2 will be 1. So our input rate will be 1 kilograms per minute. Okay, so I know the amount coming in terms of kilograms per minute. Good. So question is, again, we know Q out, the amount that is flowing out, the volume flow rate is 5 liters per minute. Now this is important. Since the input and the output flow rate are the same, I mentioned this before, then the volume in the tank remains unchanged. It doesn't change with time, it's going to be fixed. So the volume at each time is the same as the volume initially, when T is 0, and that is 1,000 liters. So my R out, the output rate, will be Q out multiplied by C out. This is the concentration that is coming out, will be the amount in the tank divided by the volume in the tank. That gives me the concentration, okay, in the tank. But of course, the concentration in the tank is what is going out. So it's the same as the C out. Okay, so multiply this by this. So Q out is 5 liters per minute. So I have that multiplied by this expression. X is X. Volume here is fixed, is 1,000. If I multiply the two, I get 5X over 1,000, which is the same as X over 200, right? I just cancel this out. So I have X over 200 kilograms per minute is my R out. So if you like, I know R in, I know R out. So my model is the X to T will be R in minus R out. And that gives me an equation governing the model, the problem, I should say. So plug in the expressions for R in and R out into equation 1, that is the X to T equals R in minus R out, we get this governing equation. So the X to T is equal to R in is 1 minus R out, which we just found out is X over 200. And then we have an initial condition for it. Remember that the problem said that initially what you have in the tank is fresh water. So there is no salt. There is no any amount of substance in it. Okay. So the amount at the time T equals 0, the amount of salt or substance is 0. So that is how we get this. Okay. Good. That is what I just explained here. So once you've set this up, the rest you can, this is easy. We know how to solve first order equations. So we just solve this and answer all the different questions. So if I go back, determine the initial value problem governing the problem, or governing the question. So we have that. All right. From there, then we can solve B and C. B says determine when the concentration of salt in the tank will reach this amount. So we need to solve the problem for X and also for the concentration at each time. And then we can use that to find B and C. Okay. So let's move to B. Solve 3. Yes. So we have to solve this. It's a linear first order equation. And we know how to solve linear first order equations, right? So rewrite this as that, which is equal to 1. Okay, so I can look for an integrating factor will be equal to E integral of my P is 1 over 200, right? So 1 over 200 T, that gives me E to T all over 200. So I know the integrating factor multiplied throughout by the integrating factor, then dt of X times this is equal to, the right-hand side, right? Which means X of T is equal to this. If I integrate that, of course, I'm going to get 200 e to the minus t, 200, and then I have e to the t plus a constant of integration, okay? If you like, this is what is out there. When you integrate this, you get this stuff. In any case, this is very easy, right? We have done this already. Now C1 here is a constant, so use the initial condition. When t is 0, x is 0. When you do that, you're going to get C1, the constant, to be -1. So you plug it in here and then multiply through and you get this expression. So you know X. X is the amount of substance in the tank at each time. So we have solved for X. So that's one of the questions. So this is what you actually want. Once you have this, then it's easy to solve the other problem. So we have the amount of substance at each time. This is just a graph of X per time, okay? The graph on the left-hand side here. So here you have initially when T is 0, X is 0, the amount of substance in the tank is 0 because it's all fresh water. There is no chemical, there is no substance in it. It's fresh water, so it's 0. As T increases, right, we see that the amount of substance in the tank also increases and keeps increasing. Here I just truncated it, right? It keeps increasing. Now, we'll see which number it approaches as T goes to infinity after a long time. Okay, good. So this is just a plot of this. The question didn't ask for the plot, but I just plotted it because it makes sense intuitively. Okay, good. Now, the question also talks about finding the concentration. All right, concentration is amount over volume. So we know the amount now, which is X. If you divide by the volume, in this case, the volume is fixed. So if you divide by the volume, that gives you an expression for the concentration. So the concentration is the amount over the volume, which is 1,000. Okay. The expression for the amount, which is X here, is given by this. We know X. So just take this and divide by 1,000. Okay. And that is what we get here. Okay. So we know the concentration as a function of time. Now, the question is that we want to determine the concentration of salt in the tank. Now, determine the concentration of salt in the, determine when, sorry. So determine when the concentration of salt in the tank will reach this amount. Okay, so all you do is that plug in the concentration there and then solve for the time, solve for T. Okay, so if you plug 0.04 in place of Cn of T, you get that. Is equal to, well, when you cancel this out, you get 1 over 5 into 1 minus e to the negative t over 200. And then from here, you want to solve for t. When you do that, you get t is approximately 44.63 minutes. So in about 45 minutes, all right, the concentration in the tank, when you start filling it, when you start bringing in this liquid, in about 45 minutes, the concentration in the tank will reach from fresh water. It now has a concentration of 0.04 kilograms per liter of stuff, of some substance within 45 minutes. That's what this is saying. Okay, good. Then the last question C, says that We want to determine the amount of salt in the tank after a long time. All right, after a long time means as t goes to infinity. So all you do is that find the limit as t goes to infinity of the expression that you have. So we know expression for x of t. So as t goes to infinity, let's call the amount x infinity. That is limit as t goes to infinity of this. Well, as t goes to infinity, this guy here goes to 0, right? So 200 times 1 will become 200. So in a long time, x will approach 200. And that is what you see in the graph here. As t goes to infinity, this guy keeps going until it approaches. This number here is 200. So it will eventually approach 200 after a very long time. Okay. Okay. So that is what this is saying. So 200 kilograms is the limiting amount. This limiting amount just means when you take the limit as t goes to infinity, is the limiting amount of salt in the tank. And the limiting concentration you can find by taking the amount, limiting amount divided by the volume, right? And that will give you 0.2 kilograms. Or if you like, you can go to the expression for concentration, right? And find the limit as t goes to infinity, right? As t goes to infinity, this guy goes to 0. So you just have 200 over 1,000, which is 1 over 5, which is 0.2. And you get the same thing, right? You get 0.2 kilograms per liter as the limiting concentration. Okay. So after a long time, note that this concentration here, that's the comment here. This concentration is the same as the concentration of the stuff that was coming into the tank. So after a long time, the fresh water will have the same concentration as the concentration of stuff that is coming into the tank. And that makes sense. Okay. So we have shown mathematically that as for a long time, you expect that from fresh water, if you're adding salt water at some concentration, eventually the concentration in the fresh and in the tank will move from fresh water to take up the concentration of the substance that is coming in, which makes sense. Okay, good. So let's finish off with the last example. This is similar to the first example, but there's a big, well, there is a big difference. So we're going to take example 1, but now we are going to suppose that the amount that is leaving the tank, all right, is now 3 liters per minute instead of the 5 liters per minute. So stuff is coming in at 5 liters per minute, but it's going out at only 3 liters per minute. So more stuff coming into the tank than you are taking out. Of course, what that means is that the volume within the tank is going to increase, right? That's what that means. So, and then we determine the amount and the concentration of salt in the tank after t minutes. So basically, we want to set up a model for this problem, and then we want to solve it for the amount, which as a function of time and also the concentration. That's what we want to do here. Good. Now, if you go back to the previous example, this curve, I didn't talk about it, but it's clear, right? The concentration is also 0 initially, and then it increases, and after a long time, it's going to approach 0.2. That is 1 over 5, as we determined, right? Finding the limit as t goes to infinity. So it's going to increase until it reaches 0.2, which is the limiting concentration. Okay. Let's go back to this. Okay, so here the volume here is going to increase with time. Okay, so we need to find out how the volume is increasing with time, because that is going to help us find the concentration of stuff in here. Remember, the concentration will be the amount divided by the volume. So we need to find an expression for the volume, how it's increasing with time, and take this divided by the volume. That gives us concentration. Then that will help us to find the C out, the concentration that is going out. Okay, good. So same thing, Q in is 5 liters, C in, that is concentration in is 0.2. Actually, this is kg. This is not L, this is kilograms per liter. Okay, the input concentration, this is a wrong unit. I'll change that. Q out is the amount going out, that is 3 liters per minute. And now we need to find what C out is, what is the concentration that is going out. To find the concentration that is going out, we need to compute the concentration within the tank, right? And to do that, we'll have to take the amount and divide by the volume. But we don't know what the volume is, right? We know initially it's 1,000, but for this problem, it's going to increase because because the output is different from the input. Okay. Good. That is what I just explained here. Now, how do you find how the volume is changing? Now, what is coming as 5 liters per minute and is going out at 3 liters per minute. The difference between that is giving you 2 liters per minute. So that at each time, t minutes, for instance, if I multiply the t minutes by the 2L, the 2 liters per minute, I'm going to get 2t. So at each time t, the volume increases by 2t, okay? So the volume after t minutes is going to be 2t L, 2t liters. So if I take the initial volume, which is 1,000, and add it to the amount that is increasing per time, I get 1,000 plus 2t liters. So at each time, the volume within the tank will be 1,000 plus 2t liters. Okay? Okay. So now to get R out, I'm just going to get the Q out, which is 3 liters, multiplied by the C out, which is the amount divided by the volume. Okay? Once again, the L's will cancel out. So I'm going to have 3x all over 1,000 plus 2t kilograms per minute. So I know R out. So I know R in from the previous example, which is just 1. That's easy to find. And now we just determine R out, the amount that is going out, output rate. So, and that is this. So dx dt will be R in minus R out. And initial condition is the same because we are still starting with fresh water. So x at times 0 is equal to 0. So good. So once you set this up, the rest is easy, right? This is just, once again, a linear equation which you can solve. So we solve it with, you find the integrating factor, which is now given by this. And then you can solve it for x of t, which is given by that. I simplify this by factorizing this out, and I get this expression here. So the blue expression here, or the expression in blue here, is basically the amount of stuff you have in the tank per time. Okay, see that is a bit different from example 1, the first example we looked at. And of course, to find the expression for the concentration, you just take the amount and divide by the volume, right? So x of t divided by the volume. Remember, the volume now is a function of time. If I divide by that, I get this expression. So the concentration change with time is given by this expression here. Okay, good. So basically, that is the end of this. But just to illustrate it, I've plotted these expressions. I've plotted this and that. So if you plot x against time, you're going to have the amount in the tank keeps increasing. Unlike problem, the first example we looked at, where it increases and then asymptotes to 200, right? In this case, it just keeps increasing unboundedly, which makes sense, right? Because you are bringing stuff, more stuff, but the stuff taken out is less. And so the volume is increasing, which means the amount in the stuff will keep increasing. Okay, so that makes sense here. You can look at the expression and find the limit as t goes to infinity. As t goes to infinity, see, this guy will go to 0, right? Because this is becoming bigger and bigger. So this will go to 0. But because of this 2t here, because of the t here, as t goes to infinity, this also goes to infinity. So the amount of stuff will keep building up, keep increasing. That's what you see in the graph. Okay, good. So that is this. But the concentration, all right, does not go unboundedly. It increases, but similar to problem 1, it will asymptote with at a long time here. I just truncated it. It will keep increasing until it approaches 0.2. See, so this is bending towards 0.2 as we found before. So even though the volume in the stuff is increasing, by the concentration, the amount per volume, okay, it keeps increasing, by increases to the concentration that is coming in. It cannot go beyond that, all right? So after a long time, the concentration will be equal to the concentration of the stuff that is coming in, which you can also calculate that here. In this case, as t goes to infinity, this guy goes to 0, and so you just have 1 over 5, which is 0.2. So after a long time, it will approach 0.2 here. Okay. Okay. So that is the remark I've given here. As t goes to infinity, the concentration approaches 1 over 5, which is 0.2, just as we found before. But unlike the previous example, in this case, the volume of the fluid and the amount of salt will become unbounded, will increase without limit. Now, this is important, which means that, well, your tank has a finite volume, right? Which means that when the volume is increasing, it's possible that the stuff will overflow. When the stuff begins to overflow, you can't use your model anymore, right? Because your model doesn't capture overflow. And so you have to know the limitations. The lesson here is that you also must know the limitations of your model. If you construct a model, pay attention to what the model can do and what it can't do. In this case, when the volume reaches, the stuff in the tank begins to overflow, the model breaks down. It becomes inappropriate or invalid to use. Okay, good. Now, this stuff is actually quite important and practical as well. They are not just for academic purposes. Okay, so this is an example I call the galamsey chemicals in a lake. Okay, galamsey stands for illegal mining. Okay, so here's the question, and it's for you to try. A lake with an average surface area of 64 kilometers squared and an average depth of 45 meters initially contains fresh water. Okay. Now, water containing an undesirable chemical from galamsey or illegal mining operators flows into the lake at a rate of 0.5 million liters per year. And the mixture in the lake flows out at the same rate. Okay. Now, the concentration Cn or Cin of T of this chemical in the incoming water varies periodically with time according to this function here, this expression here, 3 plus cos 3T. This is grams per liter. Okay, so the concentration that is coming in is changing sinusoidally. All right, there's a period where it is high, then it's low, high, according to the cosine here. Question is, you want to construct a mathematical model of this flow process and determine the amount of chemical in the lake at any time. Okay, you want to plot the solution and describe in words the effect of the variation in the incoming concentration. Well, you can assume that the volume of the fresh water in the lake is equal to the average volume of the lake. Okay, so this is just a sketch of it. All right, we know the surface area, we know the average depth of the lake. So using these two quantities, that will give you the volume of fresh water that is already in the lake. And then you have galamsey operators, if you like, this spot here, that are doing their illegal mining stuff and they are pumping chemicals into this lake. Okay, they are pumping in at a rate of 0.5 million liters per year. Okay, so this lake is becoming polluted. And so you want to know the amount of chemical that is in the lake at each time, all right? So that you will know when the levels of chemicals is too high that you don't even want, you don't want people to go there, all right? Or if you stop your illegal miners, all right, from operating, once in a while you can go and take samples, or you can use the model to tell you that at this point, this is what I expect the concentration of stuff in the lake to be. For instance, if the concentration keeps increasing every year, then of course it's likely that these guys haven't stopped. They are still working, doing their illegal stuff. Okay, so you are pumping stuff in the same rate, and the same is going at the same rate. All right, and then you want to find an expression for the amount of chemical. So this is a practical example of that. So I'll stop this video here. When I come back, we'll look at another application of first order equations, that is Newton's law of cooling. And then we'll look at another example later on the logistic model. Okay, so I will end this recording here, and then when I come back, we'll look at these